and both tenured and tenure track and senior and then junior faculty. And then this is the picture of our campus. Actually, in the advertisement, we have this picture. And then if you see my cursor, we are over here in the visualization department, and behind us is the computer science department. So we are too close to each other. Vampin is the, as Gershon mentioned, our new department head. And then also another things probably many of you knows that, like the department head of computer science is Scott Sheffer. So we have like lots of the courses like cross-listed, etc. So let me just start my talk now. So this is a very structured talk. Like I will give you the introduction, motivation, and then after that I will talk about this anamorphic Bas-Reliefs and Barycentric Shaders. Then I will just conclude my future, and then I will talk about the future work. The important thing is that this talk is really long actually. I can make it much shorter, I can make it longer. You can just design it the way you want. Like if you want, you can just stop me, ask me questions, and then it's okay. If necessary, I can speed up, because the way I structured this presentation, in the beginning, I will give you some overview. From that overview, I think most of you will understand what I will talk about, and then I will give more detail later. So basically, what I'm talking today is very different than my usual research direction. It's really a fringe research direction, and then but still inspired by the computer-aided geometric design. It's not really independent from that. And then I hope that will be like similarities will be visible on the way. And then basically the reason is that the similarity come from, I want to control the visual results the way we control like Bezier curves or B-spline curves, B-spline surfaces, exactly like that. I want to get the color exactly the way I want it. Like you see some picture here. This is actually from a painting, and then you see that I'm changing the color of it. So what I coined the word, like actually hyper-realism is a known word in the art, but I use it a little bit larger term to say that anything like representational painting or any photographic image that could be manipulated. Like what I mean is the manipulated, I will show you, like this was originally a painting by Engarni. And then as you see, we took the painting, and then we not only add the one ball into that one, there is also a sailboat. Actually, you don't see the sailboat here. And then I will show you and then you see that this become in some sense, enhanced painting. It is not the original painting anymore, but it looks like a painting. And then we not only add the stuff, we also change the time of the day, etc. Like how we can do it. So main idea here, like to use the barycentric algebra, then the whole problem become really, really simplified. And then how we use the barycentric algebra, generally it can be as simple as simply linear interpolation. Like just think about this is like a shadow computation, nothing but the shadow computation. This image is the no shadow image. This is a shadow image. And then we just mix these two images, and then we got this result. So as a result, we can turn the real photographs into something renderable, and then, but not only we embed lots of the information, like the some of the illumination information already embedded, etc. Like this is the kind of the tricks we do. Actually, this whole idea started almost 20 years ago. And then, like as I told you, I'm in the visualization department. We are not just only teaching the programming courses, we also teaching some courses which is towards the movie industry. And then in that time, I wanted to like the come up some like the digital compositing course, but some interesting course. Let me just show you that video here. So this was the first project actually on that class. Like actually this is from my original home. These are like, I still have this olive oil, probably. So the bee comes. The whole idea is we should see the reflection of the bee like this. And then bee become interested in this teapot, enters. Another is the interaction, the reflection, refraction, etc. So that's the main idea. And then I formed the class, and then I start to teach it like I offered it, and then it become like, so basically, but there was a problem in the class. Like I will tell you later, it was so complicated. So I wanted to make my students like become advantaged comparing to other people. So to be able to do these things extremely simple way, like how we can speed up the process. So eventually I came up this ideas, and then the ones I talk, but basically I created a bilinear dynamic painting. The one I showed you before is like this. So this is a different time of the day. This is almost like a morning, like maybe noon. And then this is like a sunset. And then this is the illumination information. This is the time of the day. You interpolate them like it's a bilinear interpolation. You got the final image. That's actually, this doesn't even need the separate shader. It can even be done like in the After Effects, or because you can write this equation directly in the some of the compositing programs. Because one of their problems, like actually I will not go into detail, but they don't provide a good algebra, but this barycentric algebra provides a nice framework. But not only that, our models are extremely simple. Like when you look at from the front view, it's a depth map. From the side view, you can understand this is perfectly wrong. Everything is wrong. But who cares? Actually, that was the Gershon's idea. And then I was impacted from that idea. Like as far as we keep visually the same position, their z distance is not really important, like as far as we can get that. So once we have that, and then we got this video of the animation of this particular one. You see that sailboat is moving, you see the reflection of the sailboat, etc. So this is another bilinear painting from the same artist, and then the same kind of stuff. This is Venice, and then let me show you that one is a little bit more interesting because we have the reflections also in this one. and then of course, in order to do the reflection, everything needs to be computed a little slightly carefully, but that's basically the same methodology. Now I will show you a talk from one of my students. Actually, this was the SIGGRAPH poster. Actually, many of the things I will show you, like almost every year, I have one or two SIGGRAPH posters. And then this is the latest one. And then she got the second prize with this talk. Therefore, I think it's a nice talk. And then it gives you an idea.
It's called the painterly rendering approach to create still life paintings with dynamic lighting. And the goal of this work is to allow an artist to take an original painted image and move the light source around while maintaining the painterly qualities of the original image, of the original painting. We want it to be art directable. And still life painting really lends itself to this work because it's very intentionally designed, and the composition is a key part. It's all about creating a beautiful image where the objects are recognizable for what they are through the material property. So in this Cézanne, this piece by Cézanne, you can tell that this vase is shinier than this one, and this apple is very glossy. And the reason you can tell all these things is if you look closely, the apple looks glossy because of this one single specular highlight. It's just a simple brush stroke. And here, again, the highlight that makes the entire pot look glossy is just a simple stroke. And just with that one stroke, you can tell that the blue pot is shinier than the green one because this highlight is much more diffuse. And in this piece by Sargent, when you look, you can see like, oh, this teapot is silver, this vase is ceramic, this all these pieces on the table are all silver. But when you look closely, and the reason you can tell that is because of they have specular highlights. But when you look closely, it's so expressive and it's very loose, and it doesn't have to hold up on a close hold. The piece really conveys all the material properties beautifully. And it's really interesting to see that these loose, expressive brush strokes can really convey material properties really well. And even though it's not photorealistic, it's very beautiful. So the methodology we use to preserve these, like this painterly style, is as follows. So we start with a painting, and then we create control images. So what would that painting look like with just diffuse lighting, no global illumination? And what would it look like if it was completely in shadow? Then we make the proxy geometry, being mindful of the silhouette edges. And the proxy geometry doesn't have to look good from every angle. It can be very messy, so you don't have to be a good modeler to be able to use this method. We'll then create the reflection maps, which are basically the loose expressive highlights that we saw in the previous works. So this is how we emulate those. And then we'll be projecting these images onto the proxy geometry. We use reflection planes to calculate the specular highlights. So we just have these 3 points that define a plane, and we assume that the light source is in the center of this plane. So what we do is we check if the reflection ray intersects the reflection plane. And if it does, we pull that UV coordinate from the reflection map, which is this highlight, essentially, and we map that color and the alpha value to that shading point, and that's the specular color.
The way the shader works in order to calculate the final color is we take the dot product of the normal and the light vector and see that gives us the amount of light that's hitting the shading point. We use that number in addition to this value S that's determined by the specular strength, the alpha, and the Fresnel value. We use those two values in order to calculate the final image. So the way it works is we're interpolating between the two control images, T0 and T1, based on the value T, which is the amount of light hitting the shading point. We then multiply that by the value S, and we add that to the specular image, the reflection map, which is also multiplied by S. So by interpolating between these two images, and then as a whole interpolating between this diffuse color and the specular color, we get the result, which is the final image, which blends between the diffuse and the specular for each shading point. So it looks pretty complicated, but it's actually quite simple. It looks more intimidating than it really is. And these are some of the results.
And you can layer and composite very easily, doing separate passes if you want to. And all the shadows and highlights move according to this pseudo light source, and it's temporally coherent. And then this is what the original painting looks like compared to the final render. And with that HSL adjustments I mentioned, you can change the colors of these reflections really easily if you want it to look a little bit more yellow, or if you want it to look a little more pink. It's really easy to make those changes through the shader itself. You don't have to repaint the maps every time you want to just shift the colors a little bit. So we've essentially made an art directable tool that is driven by the talent of the painter. So if you can paint something, this tool has infinite potential. So we're really putting the power in the hands of the artist with this tool, which is what's exciting about it. And in the future, I'd love to see this work in a real-time environment and to allow for camera movement, because right now it's just locked to that one perspective. Thank you.
Okay, so now that I will motivate the work. So actually this whole thing started from somewhat for me from Jurassic Park. Actually, not the whole Jurassic Park. I didn't really care about the dinosaurs and something. I like this kind of images. Like in the Jurassic Park, there was this picture, you remember, it says that objects in mirror are closer than they appear, because the guy was running And then you see the reflection of the dinosaur. Actually, there was another scene, two dinosaurs goes after the children, and then you see their reflections. Like, I like that. I thought that this is the exciting part. Like other part of the compositing, I didn't care. Like I can teach it in the very short time, because it's simply like we are doing associative alpha operations, etc. Like if you can clean up, those are what not was my intention. It was complete. The global illumination was my intention, shadows, etc. So this whole idea has been around. Actually, you know that it didn't start with the Jurassic Park. Even the George Méliès 125 years ago created the similar enhancing the images. I think probably I shouldn't call the hyper-realistic. I don't know what is the best term for that. Like image enhancement, image augmentation, this, or even the augmented reality in somewhat the same concept. Like we take some kind of the image and change it to new image, and then this image still looks somewhat reasonably believable. So when I teach this class, like and I start to see the problems. Like actually this is from a latest class, an object goes behind it, and then you see the changes in the caustic also, not just the reflection, but also the caustic. And then when I think about this problem, I think after a few years, I realized that, okay, I need to surprise the people. Then we start to include the impossible objects. So you can understand this is a virtual object. These are not the real objects, but still, when you look at it, it should look like reasonable. So that was the whole idea. So this particular one is from another student of mine, Brian Clark. Actually, this is like 2001. The other one was 2000. And then we had this, like I formalized in that time. Like we have like reflection, like the reflection, refraction, plus some kind of the interaction with the environment. So in order to solve it, they have to do something. I won't show you this video. And then both actually Brian and then Gary initially go to the ILM, and then they go to the Pixar later. Both of them are. So this is from the Gary's work. And then I put this image just to show that how important is the global illumination effect. Like the classic way, like if you think about this is like an augmented reality, or you are thinking about, you are putting this particular piece, rolling pin in the right place with the correct perspective. But if you don't have a shadow or reflection, something looks off. Like I think the perspective is I think most least important stuff. We need to create some kind of the illusion such that this whole thing should look like working fine. But when you think about the reflections and reflection and shadow, I need to know the shapes of other objects. Those are extremely important. So in order to do that, actually that was the time Paul Debevec started, but like 1999, you remember, and then he did this kind of, like we bought the bunch of like gazing balls. Initially, gazing balls were extremely expensive. Then I found it later in the Walmart, and then I bought lots of them. And then like my students was getting the structures, like with the gazing ball, get collected the data from the whole environment. They figured out the structure of it. But this is almost like huge amount of job. Like not only huge amount of the job, if you make a small mistake, let's say this boundary is wrong, then like immediately shadow position will look wrong, reflection will look wrong, and then human will realize it very, very easily. So like the problem is in the real object. Real objects are not like a perfect geometric model. Like even a sphere is not really a perfect sphere. It is a little bit off. And you cannot put them in the right place. You can always have an off stuff. Then I start to think like, why I'm doing the perspective correctly, why I don't embed the perspective into the picture. So And in the same time, when I'm doing the color values, why I'm doing the physically based stuff, maybe I can just get exactly the color I want. Because before that, students were looking this ones, and then we wrote a few paper like, how can I just estimate a nice, like the color distribution such that I can make this one corrected. These are still a big jobs. Like I wanted to something extremely simple. So this whole thing can be computed very, very easy way. It should be robust, and then we can just get the good result. Then I was thinking about the artists, like how the artists do it. Artist doesn't know necessarily doesn't know how the light behaves, but they do it. Like these are the examples, and then these are the how the word goes. Like you need to get the separation, you combine them, etc., etc. It's a huge job. So this is the example from the artist. I'm not sure this particular artist knows all the how the reflection works, but if you look at this whole image, it looks perfectly right. Like he gives us the illusion of the reality, not necessarily knowing all this math behind it. Of course, if you go through the purely correct way, probably you will find out this reflection doesn't have to be here. Maybe it will be a little bit off, but who cares? I know the reflection will be always in the high curvature regions. Like, but how I know that actually without knowing the math behind it, because we think that reflection is a different thing. But in practice, you realize that reflections are always in the high curvature regions, and then they move a little bit, but that's not a big deal. So I can make certain mistakes, but those mistakes will not affect my results. So I start to think about this way. So this is like a bunch of stuff. Like I came up with two ideas eventually. One is I want to represent the geometry with the anamorphic bas-reliefs. I will explain what I mean with that. I will represent the material with the barycentric formulas. That's the whole idea. So let me talk about the anamorphic bas-relief first. So anamorphism is really a concept of embedding the perspective into the image. So like you see that the image in the, like somebody draw it, it's like a simple image, but if you put it in right way, it looks like a correctly flying logo of A. And actually this is just simply a paper, it's cut like but bas-relief is a little bit different things. Bas-relief is like a sculpture, but you take the sculpture and then squash the sculpture like so basically what you are doing with the bas-relief, you take the actual normal vectors and then you change the normal vector. And then over there we prove that if you just change the normal vector by using formulation, all you do in the image, you change some kind of you change the image colors with the monotone formula, like monotonically increasing formula. If there was a qualitative, like the similarity concept, if two things are related each other with the monotonically increasing formula, then you can say that they are qualitatively similar. What does it mean? Let's say I have a gamma correction, I can correct my image with the gamma correction. Like those two images can be considered similar. So basically, I can take this model, squash it, get the boundaries, I can embed the perspective, and then I can use it as a model. So actually, this is not invented by like me or anybody. Like it has been known. Like if you go and then look at the Modern caves 15,000 years ago, look at the legs. These are like a three-dimensional stuff, bas-relief, and then you have foreshortening. Actually, even that time, the people thought about it. They embedded the perspective. They do a structure. I will call it anamorphic bas-reliefs. So what are the anamorphic bas-reliefs in terms of the computer graphics? One is the normal maps. So actually, you know, all this normal maps algorithm, I will show that, like the Johnston's paper, and these are much more recent papers. And then my students work on, like my initial dream was just to create some kind of the system to the people in the industry, but it was too big a dream. And then I realized that it is very hard to do it. Like some kind of the, you can think about Photoshop like environment. You build the models very easily. You do everything on that one, right? Therefore, since I see that this is too big, so right now I'm going baby steps. Like I'm just trying to. So this is from that time by using a normal map, because initially I thought that normal map is a good idea. Right now I don't believe it, and then I will show you why. Like the, so before going further, what we did in this work, by using normal map, we also computed the shadows, reflection, refraction. I will show you everything. Like the, what I was thinking, I can have a bunch of the normal maps in 3 space, and then with this, we can just get all the images we wanted. And then you will see that. Actually, this is the software. If you want, I can just put it the software. You can get it, and then you can play with it. By the way, this was one of my cartoons, and then my student turned it to the normal map, and then then we start to illuminate it.
Well, I don't know if it's a good idea to ask question now, but I mean, you don't have slide numbers, so.
Yeah, feel free to ask questions like the.
Okay, I'm wondering how did you create the normal map? How do you extract the geometry from the background?
Actually, for this creating the normal map, we created a like a small software. We just give the normal in the boundary. From that, like we created some kind of the 2-dimensional shapes actually, and then we control the normals in the boundary. Like I didn't do normal map designs like my student did it, but those can be done with many different ways. Like there was also the paper on that direction. Like this was the R work, but so I make it sounds so you can ask questions and then I can answer the questions. So let me just go a little further because there's some interesting stuff later. So like we can just create a complete, the reason is the artist can create a very strange color combination. We can do that. This is from Luma. And then more important, I can just take anybody's painting. Like I took this is a good question. Like maybe I can stop here. For this Picasso image, I sit it in front of the Photoshop and then I quickly draw this image and then I use it as a normal map. It doesn't even have to be correct. You see, it become more exotic, interesting stuff in some sense. So because the Picasso image anyway doesn't make too much sense, so we want to, so this one is a little bit easier because I know the directions of this, and then we can just get those ones. Once we get the directions, we can compute the ambient occlusion, we can compute the shadows, and then you see that it looks somewhat believable. And there's more interesting images like later, therefore I'm showing you this. Like there's another one. This is the lumos, and then you can see the reflections in the nose and then eyes, and then we can choose that one. This is extremely simple method actually. We have only 3 images, and then some, by using the alpha map, we just define them as a reflective, etc. And then the same way, like this is from cross shade paper, and then you see that I make this one slightly different. This is the one image I love a lot, because I look at this Warhol's Campbell soup. Everybody thinks that this is extremely simple image. Actually, it is not. He had the reflections here, and then he has very subtle diffuse illumination. I went through the image, and then if you look at it, we capture exactly the way he does the. But when you look at each image, looks like his image, but so we also did this kind of the complicated stuff like eyes, and then you can get the. So let me go to the next one. Next one is, okay. Then here we did I started to think like, what is the advantage? That was my initial thinking. If I have let me just, not to put the sound. If I don't have a normal map, the advantage of the normal map, my functions like vector fields do not have to be gradient field. If they are not gradient field, I can do the things which I cannot do in real objects. It goes beyond that. But not only that, like whatever you see here, like Fresnel information, etc., none of them are realistic. Everything is just slightly similar or qualitatively similar versions of the actual ones. So therefore, we are able to get that, but still, like everything looks like a hand-drawn, painted, etc. Like there's more example here. This becomes also a poster. So there is we can put the environment here, and then you can just, I can get a different feeling, like this background image was another image from the digital compositing class. I used that one as a background image here. Like you can see that we can change the index of refraction, but the index of refraction is not really correct, but it is somewhat correct. We can change the translucency or transparency. These are all real time because it's very, very simple mathematically, because what we did was, so all of these ones are in the internet, like what I will show you right now. Okay, we just go to the. So if you go to the Mach3D tamu.edu, this is the first piece I show you. Like you can play with it, and then you can play with all this function, but I will show you something else. Like that will be the second one. So here, my next idea was, I realized that normal maps are not good enough. So if I want to do something better, I need to have a depth map. So this is an example from the depth map. Like I will just put and then I will, you see that I can get the subsurface scattering in the real time, and then just using WebGL. And then this algorithm is extremely simple algorithm. Like I came up with some, again, the formula, it just gave you we have so many, the ways, we can change the colors here, and then we can also put the environment light, we can change the light intensities, etc. But therefore, the depth maps are really useful. Actually, those depth maps do not have to be really good. Like we can just get those depth maps from any depth information, and then we can directly use here. So there are several of them, like the Buddha is like this, etc. Like we can see them. And then all we did was we get the actual three-dimensional model, we just turn it to the depth map and then use it here. Okay, let me go back to the PowerPoint presentation. So let me, okay. So as I said, that depth map can be an ABF, and then I show you this example, and then this is the Mach 3D, what I show you to you. And then the other one is the 3D models as the anamorphic Bas-Reliefs. That was an example. Like I will talk about right now, the barycentric formula, why that's important. So actually I have a bigger example. And then why we need the barycentric algebra? That's really the key question. So this is from a I think this is 2016 paper in the expressive conference. We show that actually this image, I had it for a long time. I didn't check it. When I check it, I found out this is the shadow. The reason is that I took these pictures by using colored light. Like let's say that I have a red, green, blue lights, and then like because I wanted to show my students actually shadows are not really gray colors, they are colorful. But when I took that pictures, I never look at the actual numbers. When I look at the actual number, I found out this was the non-shadow region is the 200. Look at the red value. Shadow region is 214. This is counterintuitive because your photography process is not necessarily linear process, and then you end up with something. If I make any kind of the monotonic increasing function changes this number is still bigger than this number. So I cannot change it. So the only thing I can do, I need to create a similar correspondence in the images. So in order to do that, the only way, like classical like formula based on the vector-based formula, because it can never be negative number and cannot create this. But the barycentric formula created. And then look at the example, another example here. This color is the 100, this color is 108. This is bigger. Look at this one. This is 222. This is 220, 230. This happens even in the photographs. But if you go to the artworks, it's much more crazier than this. So if we want to do this, we cannot just use the physically based approaches. So this is the mathematical reason. Our classical formula is like this. I have a color, and then I'm adding a vector to the color. But we need to think about the color as a point. I have to interpolate the color. But when I think about the interpolation of the colors, we can separately interpolate them. Instead of a convex hull, we have in the convex box. So basically, our methodology, instead of working with the convex hull, it creates a convex box but at this I cannot go anywhere, and then I cannot create the things I don't want, but also I can be very much in the control. That's the whole idea. So this is from this paper, and then we have the bunch of papers. Like as I said, that almost every year we had a few papers showing that. But of course, I wanted to show that the methodology works for a variety of styles. Like in this case, this is a reflection, like a Chinese painting with reflection. It works. Like here, we had the charcoal with reflection. And then, so this one was, but of course, in each one of them has a different solutions we came up, but the basic idea was always the same. So we have some kind of the barycentric formula. Depending on the case, we had a different barycentric formulation. For instance, if you do the cartoon shading, it's better to use the like a 0-degree B-splines. If you want to have a different kind of, depend on what you want to do. Like this is another one, the cross-hatching, and this one is a relatively recent paper. Like there was another painter, like a Western painter, we just did that difference, like the date is changing, that kind of thing. And then this is a new one. This is not like my students is working on the capstone project. What we try to do, in this case, we are not using the anamorphic Bas-Reliefs. These are the three-dimensional model, but this shows that how complicated it can be. Like the Georgie O'Keeffe here created so many different colors. Like This is a shadow color 1, shadow color 2, border color, color 1. So what we did was we eventually figured out the best way to separate everything. Like I have the light 1. Light 1 have a cosine theta. Light 1 has a shadow. Light 2 has a shadow, and then cosine theta. Based on that, we created extremely complicated, you can think about the formula, but actually the formula is very simple. Like first we need to start with some kind of the Bezier function. The reason is that we want to interpolate the first and second. The second, like we wanted to have these two colors, and then this almost the same. So we ended up a nice looking control on that one. So we could use a slightly different formula, but the basic idea is the same. For instance, this could be a first degree B-spline or NURBS, etc. We may be able to get the similar result, but we just choose the Bayesian. So this is, you see the difference between, if you use the linear, you don't get the same result. Then we get each term, like specular term. Like we make the one, another, like barycentric formula for the specular term. Another term is the shadow color. Another term, border color. Border color is a slightly, we did it a different way, like from the eye, we shoot the rays. And then from that, we understand this, is this positions on the shadow according to the eye position, and then we randomize it. That gives exactly the way the Georgia O'Keeffe did. We get another formula, like we are just doing it again and again. And then like, let me just go through this, like this is almost the result, like after all of them finished, we got the final result. And then you see that so you get the idea in general case, like we come very close to Georgia O'Keeffe, and then you can see this thing, like this is like a three-dimensional models. Oh, that doesn't work. Okay. So obviously I didn't take when I copied the file, I didn't copy so these flowers are moving around, and then when they move, they still look like a Georgia O'Keeffe. The reason, the trick is, in this case, we didn't use any texture. Everything is a color. Only with the color we were able to get the approximation of the Georgia O'Keeffe. Now I will just give you I hope I am on time. Okay, I'm in good shape. So what I believe the anamorphic bas-relief and barycentric shaders like can provide us a very good framework. Let's say I want to do any real-time interactive augmentation operation. Like I can do that because I can collect the let's say depth information in some way. Like it can be even from the depth cameras, or I can just get it from by using some computational neural network, etc. If I get the boundaries right, that's the key idea. And then for barycentric shaders, if I can get the intrinsic information correctly, so I may be able to create illusion of the realism like in real time. What I was thinking, so let's say that I'm wearing like an AR glasses. I don't have to. I can have a VR. I can just take the information from the scene. I can just change it. I can turn it to artwork. And then I can add the new objects and shadows, reflection, refraction, caustics. Everything will look okay, but I can do it in the extremely fast. Right now in the movie industry, this is extremely expensive kind of the operation. And then the reason I'm saying it's an art directed, as I explained to you, like none of my Fresnel equations, even this, like my specular reflections are correct, but don't forget that I may not get the specular reflection from the right places. Those are even somewhat wrong. Reflection equations, I'm not exactly using the classical reflection equation. I change it a little bit such that, like, not to use the square root, etc. Like it become much simpler reflection equation. But the humans do not have a good idea about, as far as we can get the qualitatively correct information, this can be done. Of course, if I use the directly correct refraction, it will still work, but I wanted to make everything faster. Not only that, Fresnel, I'm not using the exact Fresnel, and then like exact Fresnel, I can show you this maybe here. So let me draw. Like exact Fresnel looks like this. It goes down and then goes like this. My Fresnel looks like that. So why I did it that way? By using this, I can just play this position, and this position in control. Like if I want to do something, why this is important? Because if you look at the bottle like this, generally this part is reflective, this part is reflective, this one is refractive. So if you want to have a complete control, you want to make this area a little bit more visible, you do it like this. But if I use the exact Fresnel, I don't have an artistic control. So by doing it, like it is simple equation, and then I can still get the something look like Fresnel because we know the qualitative how the Fresnel works. So this is an example. So another okay, another example is this beautiful Edgar Payne like image. He has such a beautiful like shadow regions, reflections, like in the water. You can see those colors are really important, like to get the beautiful result. Like we can even go to a place, wear a goggle, and we can see it as a painting. It will look much better than what our experience. And we can do it in the real time. All we do is like, we need to process the data. We create a new image and then show that image. If we can do it in the fast enough, and then I expect it will be eventually, we will be able to do it. Not only that, like let's say that if we want to understand how the color blinds see the world, like we can just in the real time, we can change it. Like this is an illustrator who is the color blind. You see that his painting is different than the non-person. Like if I want to understand the experience of the color blinds, and then I can wear it, and then maybe we can just create some specific application for the color blind, they can see it better. Or of course, I'm thinking not only that, like I'm doing some operation, like it is not simply just showing them the visualization. Like these things, the one you see on the right, these are done by the professional artist. Actually, a friend of mine was a doctor. He was a cartoonist. And he studied, after he became a medical doctor, he studied and then become a medical illustrator. He's in Australia right now, and then he's making like just as a medical illustrator. Like this is such a difficult job, just to be able to show the people exactly what is going on here without any confusion, etc. Let's say, can we do this kind of stuff? Like, but in order to do that, we need to think about like a medical illustrator, how they do it, from their experience. We should understand. Like you see that they don't really simply use the very dark shadows. They make it slightly darker. That's what I'm trying to do. Like, so it's a methodology. So that's so I have too many videos. Like I think all this videos and everything is in the PowerPoint. If you want, you can just go and then download them. You can see them, etc. So that's all. You can have the questions, and then I can try to answer the question. Let me.
Thank you, Ergun. So it's really exciting. I really like this stuff. Let's see if people have some questions while they can get ready to ask. Ergun is going to share with us kindly all his material indeed, so you can pretty much browse through his PowerPoint slides and so on. So questions, anybody?
Mhm.
Let me start with a